Just want to check if everyone, if you can hear me, if you can just put some comments in the chat box. Just confirm if you can hear me. Okay. Thanks. Thanks very much. Thanks everyone for confirming. I'm just accepting more people into the session. Once again, thank you for joining us. And just before we start, I just want to share some instructions here. If you can just follow these steps, just ensure that you enable the sounds and notifications so you don't get any form of disturbance when you are trying to listen to the session. So if you can just follow the instructions there. Thanks. Some common questions, more especially for those who are joining us for the first time. So regarding the copy of slides and the recording, we will be sending this to each and every single one of you to your emails. So just ensure that you look out your emails in the next 2 business days. Just make sure that you also check under junk or spam folder, because sometimes it doesn't really go straight into the inbox. So just check in there as well. Certificate of attendance. Yes, we will be providing a certificate of attendance to everyone. So how it works is you will have to be with us up until the session. I will be sharing a link or a QR code that you need to follow in order to claim your certificate of attendance. Unfortunately, if you haven't done so, we cannot be able to provide you with the certificate. So you need to ensure that you follow some instructions at the end of this session so you are able to claim your certificate. And yeah, we do try by all means to send it out at least within the next 4 business days. So just yeah, stick around for more details on how to claim your certificate. And just for those who are joining us for the first time, my name is Peridi Kotla. I am based in the South African office. So just for those who are joining us for the first time, just give you some background about EIT and what we do. I always say when you think of engineering, think of EIT. So we specialize purely on engineering. As you can see there, we start with like short courses. Those are our micro-credential programs, professional certificates. We've got diplomas, advanced diplomas, undergraduate, graduate certificate, bachelor's, master's, and then our highest level of qualification is Doctor of Engineering. There are so many reasons why people choose EIT, choose to study with us. But I believe what normally stands out is that we are delivering industry-orientated programs. That what you learn at EIT today is something that you can immediately implement in the workspace. We are just like any higher education provider in Australia. So our courses are created with Australian government. And then secondly, we have some of our programs that are registered or recognized under 3 international engineering accords. We source our lectures from different parts of the globe, and doing so, we also give our students an opportunity to have sort of like a global perspective when coming to engineering, and also to connect with students or friends, peers in various countries. And we're doing so by also making use of a very unique method of delivering courses through webinars, interactive webinars. When coming to practicals, we make use of simulations, advanced technology in remote labs as well. So for that being said, yes, just to sort of like going back to what we've been talking about, why students choose EIT. So this is one of the KILL survey. So you'll see that there are so many reasons why people study or choose to study with EIT. We've collected some accolades last year, in 2021, 2024, and I'm sure that it's sort of like also a complement from the previous slide on our commitment to ensuring that we provide quality education to our students all across the globe. And on that note, I'm now going to introduce my colleague, Saide, who is now EIT lecturer, and obviously she will be covering lots of important information on big data analytics in power systems. Then I'm now going to hand things over to our presenter for today, and feel free to make use of the chat box channel, just in case when we get to some questioning there. Today, I guess you can take it away. Thanks. Hello, hi Sade.
Yep, thank you.
Okay.
But yeah, I couldn't see the slides, unfortunately.
Yeah, I think it was still loading. Can you see the slides?
Oh, okay.
I'm sure it should be loading.
Yes. Thank you.
Okay, perfect.
Yep, thank you. Hello, everyone, and welcome to this webinar on big data analytics in power system. In the next hour, we'll look at how big data is being collected, processed, and used in power system. I'm Saide. I'm a lecturer in electrical engineering at EIT and a researcher with a background in applied mathematics and system analysis. My work focuses on applying artificial intelligence in both healthcare and engineering, and I specialize in using AI and deep learning for medical image analysis to support better diagnostics and clinical outcome. I've also been involved in the project related to data analysis, computational modeling, and image processing. Okay, before I start, let me walk you through what we'll be covering in today's sessions. First, we'll begin with a broad overview of how big data analytics is transforming power systems, why it's matter, and what kind of data are involved. Next, we'll explore the data collection, cleaning, and storage techniques that makes big data analytics possible. And then we'll shift focus to the heart of analytics, the method and the machine learning applications that uncover patterns and supports. And finally, we'll reflect on the challenges and future directions. Now, let's talk about why big data is so important in today's power system. First, we have to recognize that modern power grids are becoming increasingly complex. We are no longer dealing with a simple one-way flow of electricity from large power plants to consumers. Instead, we are now managing multi-source energy networks with renewables like solar and wind, battery storage, electrical vehicles, and even a consumer-level generation like rooftop PV. All of these introduce variability and complexity. That's where big data step in. It plays a central role in helping operators and engineers manage this complexity by enabling real-time monitoring, predictive decision-making, and data-driven optimization. Let's go through some benefits of this big data. First is efficiency. With access to real-time and historical data, utilities can optimize energy distributions and ensuring the right amount of power is delivered where and when is needed. Next is reliability. Big data enables predictive maintenance by analyzing trends in equipment behavior, such as transformers or circuit breakers, and identifying sign and wear of the failure before they cause outage. And also, the important parts. We have a cost saving. Real-time data analytics help reduce the operational costs by minimizing downtime, automating response, and even adjusting pricing or load in a smart way to lower peak demand. So big data is not just a technical add-on. It's becoming a core enabler for smarter, cleaner, and more resilient energy features. Now, let's see what the challenges in the power system. While big data offer different potentials for modernizing the power system, we also need to talk about the challenges. First off, there's a demand fluctuations. While the growing presence of the renewables like solar and wind electricity generations has become more variable, combine that with unpredictable consumption patterns from EVs and smart appliances, and it becomes harder to match supply and demand in real time is the problem. Then we face the issue of agile infrastructures. Many components in the grid like transformers, cables, and substations were never designed to handle this level of data communications or distributed energy inputs. So integrating big data into the legacy system can be complex and costly. Another big challenge is data overload, because power systems generate terabytes of data every day from smart meters, sensors, also a weather feeds. But without the right tools and strategies, this data becomes noisy rather than insights. And security is another critical concern. And also, we have some general threats, both physical and digital. And ensuring resilience in the face of these threats requires not just technology, but also robust planning and real-time situational awareness. Now, let's take a moment to define what we really mean by big data, especially in the context of power system. Big data refers to a large and complex data sets that are too massive and too fast-moving to be handled by traditional data processing tools. We are talking about terabytes and sometimes petabytes of information coming from smart meters, sensors, satellite feed, or the other sources. To better understand big data, we often describe it using 5 V's. First, there's a volume. This is about scales. We are dealing with massive amounts of data, often arriving every second from distributed assets across the grid. Then we have the variety. Data in power system isn't just one format. It can be structured, like tables of the voltage readings, or unstructured, like images from inspections, drones, or consumer complaints on social media. The third V is velocity. It's the speed at which data is being generated and needs to be processed. And many power system decisions, especially those around the grid stability, require real-time analytics. Next is veracity, which refers to the trustworthiness and accuracy of the data. Bad data leads to bad decisions, so validating and cleaning data is critical. And finally, there's a value. All this data is only useful if we can extract meaningful insights from it, whether that's detecting faults or forecasting demand or improve asset performance. Now, let's look at why analytics is such a powerful tool in the world of the power system. First, it supports enhanced decision making. Traditional approaches often rely on historical data or fixed rules. But with real-time analytics, operators can make a smarter and faster choice, whether that's rerouting the power during a fault or balancing a demand across a region. Next is optimization. Power systems must operate within a maximum efficiency, both economically and environmentally. Analytics help utilities fine-tune energy distribution, reduce losses, and manage generations more efficiently. Another key benefit is the predictive insight. This is where machine learning comes to play. By recognizing patterns in the data, analytics can forecast when demand will spike or when transformer is likely to fade. And finally, we have a risk management. Power systems face all kinds of risks, from cyber attacks to equipment failures and weather disruptions. Data analytics allows us to quantify and monitor these risks so we can take actions before they escalate, whether it's identifying weak points in the grid or flagging suspicious access to control systems. When we talk about analytics in big data, it's helpful to break it down into the four main types, and each answering different questions, from understanding the past to planning for the future. Let's start with descriptive analytics. This is the most basic form, and it answers the questions: what happened? It helps us summarize historical data, things like how much power was used last month, how many outages occurred, or what the peak demand was yesterday. This type of analytics gives us context and patterns. Next, we have diagnostic analytics, which takes a step further and asks, why did it happen? For instance, if we see a sudden spike in power consumptions, diagnostic analytics might link it into the weather conditions or change in industrial activity. It uses correlations and root causes analysis to identify drivers behind the trends. Then comes predictive analytics. This is where it gets exciting. It answers what will happen. Using statistical models and machine learning, predictive analytics can forecast electricity demand, predict equipment failure, or estimate the impact of upcoming heat waves on the grid. And finally, there is a prescriptive analytics, which addresses the question, how can we make it happen? It not only forecasts possible outcomes, but also recommend specific actions. For example, it might suggest the optimal load shading strategy during a supply shortage, or the most efficient way to dispatch the generators. This level of analytics supports automated and strategic decisions making. Together, these four types of the powerful toolkit helping utilities move from simply reacting to the event to actively shaping outcomes through a data-driven insights.
My apologies if you said again. I'm just asking if I could please just reshare the slides. They seem to be quite a lot of people.
We have discussed the types of the analytics. Let's look at some key benefits that big data analytics brings to power system. First is reliability.
Hi, Sadia. Hello?
Big data analytics help improve the stability and uptime of the grid by continuously monitoring the system in real time and predicting failure before
Sadie, can you hear me?
Next is cost effectiveness. As we mentioned earlier, throughout the data-driven optimization, utilities can reduce the operational expense. For example, analytics can identify inefficiencies in generations or transmissions, suggest better maintenance schedules, and even automate control decisions, and all of which contribute to the lower cost. Then we have sustainability. With the global push of the cleaner energy, integrating renewables like wind and solar into the grid is crucial. Big data analytics help forecast their output, balance loads, and optimize storage and dispatch. And there are also some important additional benefits. Analytics enable faster response time when issues arise, and instead of waiting for a problem to be reported manually, automated alerts can pinpoint anomalies in real time. And from the customer's point of view, this translates to better service, fewer delays, more accurate billing, and higher satisfaction.
Hi, Sadia.
To thoroughly understand how big data creates value in a power system, it's important to look at the analytics life cycles. The journey data takes from collections to actions. Let's walk through here briefly, and then we'll go through the slides in details for each part. First, we have a data collection. This is a starting point. We gather data from different resources. Then we have a data cleaning. Raw data often includes missing values, outliers, or noise. Then once the data is cleaned, the data is stored in a suitable infrastructures, maybe a cloud database or a distributed data lakes. Next step is data analysis. Here, where the insights begins, we might apply machine learning algorithm to detect patterns and indicate the transformer is starting to degrade. The decision making is the next step. The insight gained are now used to make decisions. And feedback loop. This is a critical, often overlooked step. After maintenance actions is taken, we feed the results like whether a fault was actually found back into the system, and the feedback helps improve the model over the time and making the future predictions more accurate. Now, let's focus on the first stage of the big data analytics life cycle, data collection, which is absolutely the foundational for everything that follows. In power system, data comes from a wide variety of sources, and understanding these sources helps us appreciate the scales and complexity involved. First, we have sensors. These are deployed across the grid, continuously monitor variables like the voltage, current, temperature, pressures, and vibration. For example, sensors on the transmission lines can detect overheating or line sag, giving us an early warning before failure occurs. Then there are IoT devices. Internet of Things technology has brought intelligence to all levels of the grid. A smart meter in homes, for instance, record details energy usage every 15 minutes and send that information back to the utility. And this device also enabled a two-way communication, which is important for demand side management. Another important source is historical data. This includes records of the past outage, load curves, maintenance logs, and weather data. Historical data is especially useful for training machine learning models and identifying long-term trends. Now let's talk about the data variety, because as we mentioned earlier, not all data looks the same. We deal with structured data like a spreadsheet and SQL datasets. You can think of a neatly organized table showing hourly power consumptions for each customer, for example. But we have also unstructured data like images from drone inspections of the power line, or PDF reports, or even a customer service call transcript. This data may not fit into rows and columns, but it still holds valuable insights, especially when analyzed with modern tools like the natural language processing or image recognitions. So data collections in power system is about gathering the right data from the right places at the right time. The better our data collection process, the stronger the foundations for accurate analysis and smart decisions making down the line. Even with all the data we can collect in power system, quality matters just as much as quantity. If the data we feed into our analytics systems is flawed, we risk making a poor or even dangerous decisions. Here we have some key challenges in maintaining high data quality. First, there is incomplete data. Imagine you are monitoring power usage from smart meters, and one meter goes offline for a few hours. That gaps in the data could throw off your demand forecast, especially during the peak times. And missing entries can easily lead to inaccurate predictions. Next, we face inconsistent data. Power system data often comes from multiple sources, SCADA systems, IoT devices, weather feeds, and so on. These systems might use different formats or reports value in different time intervals. If the data isn't harmonized, it can conflict or making analysis unreliable. Then we have to consider real-time accuracy. This is especially important in critical infrastructures. If a voltage sensor reports a value within a delay or worse, with a time synchronous error, operators might act on outdated information. So ensuring that real-time data is reliable is a key to safe and responsive operations. And finally, there is the issues of data redundancy when the same information is recorded by multiple systems, say smart substations and a central grid management platform. You can end up with duplicate entries. This not only waste storage space, but can also skew the analytics if they are not properly filtered. Once the data is collected, the next important steps is cleaning it, because dirty data can lead to a bad analytics and poor decisions. Let's go over a few key techniques used in cleaning process, especially in power systems. First is data imputation. This is how we handle missing data. Instead of ignoring gaps, we fill them using statistical methods. For example, if a smart meter didn't record the energy usage at 2 p.m. due to a signal loss, we might estimate the missing value based on surrounding data or average usage at that time of day. Next, we have normalization. This is about making sure data from different sources is on a same scale or format. Imagine one sensor reports voltage in kilowatts and another in volts. So without normalization, the systems would treat them as incompatible. Standardizing ensure data can compare and aggregate accurately. Then comes to the error detections and corrections. Sometimes devices malfunctions and report extreme or impossible values, like a transformer suddenly showing a temperature of 2000 degrees C. We use logic, threshold, or machine learning to flag these errors and correct them based on known behavior or expected range. And finally, there are data duplications. This involves removing duplicate entries, which often happen when multiple systems log the same events. For instance, both SCADA systems and IoT devices might record breaker faults, and if we don't duplicate, we might double count the events and skew our analysis. After we collect and clean data, the next question is, where and how do we store it? This is a huge challenge in modern power systems where data is generated constantly and at scale. Let's walk through the key requirements for an effective data storage solutions. First, we need scalability. As more smart devices and sensors come online, from substation to solar inverters, the amount of data being generated grow exponentially, and our storage system need to scale upstream seamlessly, whether we are storing terabytes or petabytes of data. Next is high availability. Power systems operate 24 hours, 7 days. So the data has to be accessible all times. And downtime is not an option. This means using cloud platforms or distributed systems that offer redundant backups and failover of the machines to ensure continuity. Then there's a low latency, especially is important when dealing with a real-time application like grid monitoring or fault detections. A storage system must retrieve and write data quickly so the analytic engines can make decisions within the milliseconds if needed. And finally, data redundancy. This means storing multiple copies of the data across different locations or servers to prevent data loss due to the hardware failure or corruptions. When it comes to storing the massive volume of the data generated by power system, choosing the right storage solutions is important. So it's not just about where the data goes, it's about how easily the storage can scale, how secure it is, and how quickly data can be accessed. We have three main options. First, we have a cloud-based storage. This is the most flexible and scalable options. You can quickly extend your storage capacity as your data grows, and you don't have to manage the physical infrastructures. Next, we have on-premise solutions. This means data is stored locally on servers managed by the utility organization itself. It offers greater control and security, which is important for organizations with strict data governance requirements. And we have some hybrid solutions. This is a combination, the best of the both worlds. For example, a utility might store real-time operational data on site for a quick access while archiving the historical or less critical data in the cloud. And this gives a balanced approach and offering both security and scalability. Now, let's talk about machine learning, which is one of the most powerful tools available for working with big data in power system. Machine learning is a type of artificial intelligence that allows systems to learn from data rather than being explicitly programmed. Instead of writing rules by hand, we train models on historical data so it can make predictions, detect patterns, or automate decisions. So why is machine learning useful in power systems? First, machine learning can automate complex data processing tasks. Power system generated massive amounts of data every second, and manually analyzing this data would be slow and inefficient. So machine learning model can quickly scan through the data and identify the patterns. Second, machine learning provides a deep insights from large drivers data sets. For example, in load forecasting, machine learning can consider variables like time of delay, weather, season, and so on. And also, machine learning enhances decision making. It supports grid operators by providing real-time recommendations, such as suggesting corrective actions when voltage levels drop in specific regions. Now, let's introduce the different type of the machine learning. We have supervised learning. This is the most common type. It uses labeled data, meaning we know the input and the correct output. And the model learns to map inputs to output and predict outcomes for new unseen data. A good example in power system is predictive maintenance that we'll cover in a subsequent slide. Next, we have unsupervised learning. Here, the data is unlabeled. The model's job is to find patterns or grouping without knowing what the correct answers are. A classic example is clustering customer energy usage patterns. The model might group the households into clusters such as high usage versus low usage customers based purely on the behavior. And this helps utilities design better tariffs, target energy saving programs, or detect abnormal consumptions that could signals tampering or faults. And finally, we have reinforcement learning. This is based on systems of the rewards and penalties. The model learns by interacting with its environment and improving its decisions over time. An example here would be optimizing power distribution in smart grid. The system makes decisions about how to route a power based on demand, supply, and cost, and over time, it learns which actions lead to better performance, lower losses, or greater efficiencies. We have different machine learning algorithms that usually we use. For supervised machine learnings, we use linear regressions. It's one of the simplest methods. It's great for predicting continuous outcomes, like forecasting future energy demands based on historical usage. We have logistic regression. It's used for classification tasks, such as predicting whether a transformer is healthy or faulty. K-nearest neighbor is an intuitive model that classifies new data based on closest examples it's seen before. Decision tree build flowchart-like structures to make decisions based on input features. For example, determining if an alert should be triggered based on sensor threshold. Support vector machines or SVMs are more advanced and work well when you need high accuracy in distinguishing between two or more classes, like detecting fraud in electricity usage. In unsupervised learning, we use K-means clustering. It's a common approach. It groups data based on cluster based on similarities. Now, for example, you can use K-means to segment consumers based on their energy usage habits. For reinforcement learning, the algorithm learns through the trial and error. It's ideal for control problems like optimizing power distributions in a smart grid to balance a load while minimizing losses. And finally, we have neural networks and advanced techniques. Deep learning is here. Deep learning involves multiple layered neural networks and is excellent for tasks like fault detections in complex systems or analyzing imagery from power line inspections. And natural language processing, or NLP, may seem less obvious in the power system, but it's useful for extracting insights from maintenance reports or operator notes or customer feedback. Each algorithm has its strengths and ideal applications, and choosing the right one depends on the nature of the data and the problem you are trying to solve. When we apply machine learning and data analytics in power systems, we need the right tools to process and analyze large scales and high volume data efficiently. Here you can see some of the most popular and powerful tools. Let's begin with Python. Python is currently the most widely used programming language for data analysis and machine learning. It's popular because it's easy to learn, has a huge support community, and includes powerful libraries like Pandas for data manipulation, scikit-learn for machine learning, and TensorFlow or PyTorch for deep learning. Next is R. R is particularly strong in statistical analysis and visualizations. It's often used in academic research and analytics-heavy tasks where data exploration is key. In power systems, R can be used to create interactive dashboard or time series analysis to understand consumption patterns or outage trends. Then we have Apache Spark. Unlike Python and R, Spark is designed for big data at scales. It's used when you are dealing with terabytes or even petabytes of data. For instance, analyzing sensor data from thousands of devices across the grid. So, what are the benefits of using these tools? First, they enable large-scale analysis from real-time monitoring to long-term forecasting. Second, they offer libraries and frameworks that are already optimized for machine learning and statistical modeling. And third, they make it possible to build and deploy machine learning applications directly in power systems, whether it's for anomaly detection, consumer segmentation, or system optimizations. Like the algorithms, choosing the right tools often depends on the scales of the data, complexity of the task, and the skill sets of your team. Now, let's go through some of applications of big data and machine learning in power system. One of the most powerful applications of the big data is predictive maintenance. The goal is simple but incredibly impactful. We use data to predict equipment failure before they occur. Instead of waiting for something to be break down, we forecast when it's likely to happen and fix it in advance. Predictive maintenance significantly reduces downtime and maintenance costs. Traditional maintenance is either reactive, meaning we fix things after they break, or scheduled, which can lead to unnecessary replacement. But predictive maintenance is data-driven. It ensures maintenance happens only when needed, which saves both time and money. It also helps extend the life of the equipment because by detecting early signs of wear and tears like increasing vibrations or temperature anomalies or even pressure fluctuations, we can intervene before the damage becomes critical. That means fewer breakdowns, fewer emergency repairs, and better system reliability. We rely on sensor data for predictive maintenance. that comes from the equipment like transformers, breakers, or generators. This could include temperature readings, oil analysis, current and voltage measurements, and so on. And machine learning models analyze this time series data to find patterns that indicate degradations and forecast the likelihood of failure. A practical example would be transformers in substations. By continuously monitoring the temperature and dissolved gas level, we can build a model that flags abnormal conditions. This helping prevent transformer faults that could lead to costly grid outage. The next applications is demand forecasting. The purpose of the demand forecasting is to ensure supply matches demands. If we underpredict, we risk blackouts or overloads. And if we overpredict, we waste resources by overproducing electricity that isn't used. So accurate forecasting is essential for maintaining balance and reliability in the grid. There are two main techniques commonly used here. First is time series analysis. It's involved examining historical data to identify trends, seasonal variations, and repeating patterns. For example, we might see that demand spikes every weekdays, morning, and dips overnights, or that usage is higher in summers due to air conditions. Second, we use machine learning models to capture more complex relationships like how temperature, humidity, and even major sporting events affect electricity consumption. Accurate demand forecasting helps prevent grid overloading and avoid blackouts and ensures the resource like fuel and generation's capacity are used efficiently. It also allows the utilities to schedule maintenance during the low demand periods and plan energy purchase more cost efficiently. Another applications of big data in power systems is real-time monitoring. The importance of real-time monitoring cannot be overstated. Power systems are complex and dynamic. Things can go wrong in a second. With continuous tracking of key grid parameters, we can detect issues instantly. Real-time monitoring involves tracking variables like voltage, currents, frequency, and so on across the networks. It also includes event detections, identifying voltage dips, load imbalance, or frequency deviations, all of which could signal grid instability or even a potential blackouts. These insights are displayed on operator dashboards, much like the ones shown in the image here. If something goes wrong, for example, a substation's overloads or a generator trips, alerts are triggered in real time and operators can respond immediately. And the outcome, it ensures the reliable operations of the grid, improve safety, and reduce the response time to any issues. For example, let's say there's sudden spikes in demand in one part of the city. Real-time monitoring systems detect that substations in that areas are approaching overload. The system automatically redistributes the load across the adjacent substations to prevent tripping, all while operators are notified to investigate further. This level of the visibility and speed is only possible because of the real-time data streaming and analytics, which have become essential as the grid grows more decentralized and complex. So real-time monitoring acts as the eyes and ears of a power systems, ensuring that we not only know what's happening, but can act as it happens. Another applications of the machine learning in power systems is anomaly detections. The objective here is to automatically spot irregular patterns in the data that may include faults, malfunctions, or inefficiencies in the systems. The methods typically involve using machine learning models to learn what normal behavior looks like based on historical data. Then the model monitors real-time data and flags anything that deviates significantly from normal patterns. For example, if a distribution transformer normally operates at a stable temperature and suddenly begins to show a temperature spike even before hitting the critical threshold, and anomaly detection systems can arise and alerts. And this gives maintenance teams time to investigate before a serious fault occurs. We have some benefits here. First, it helps improve grid stability by detecting abnormal behavior before it causes. Also, it enables early fault detections, and it reduces the burden on the human operators who would otherwise have to fit or have to sift through the lots of data to identify which parts has the irregularities. The next one is the optimizing energy distributions. The goal here is to balance the supply and demand efficiency across the grid. This means making sure we generate just right amount of electricity, not too much, that we waste energy, and not too little that we risk the blackouts. Here, we use two main techniques. First, we apply machine learning models for load balancing. These models can learn from past load data and the system behavior to distribute energy more evenly across the networks. And second, we combine demand forecasting with real-time adjustment, and by predicting whether and when electricity will be needed. For example, anticipating spikes in demand in residential areas on a hot afternoon, the system can adjust power flow in real time. And this is not only prevent overload, but also reduce a strain on the network. The impact of the optimization is huge. It helps to minimize the energy waste, reducing transmission losses, and make better use of the available resources, like using solar power when it most abundant, or avoiding unnecessary generator use. Okay, as we bring everything together, let's take a look at a bigger picture. How all this technology comes into play within a smart grid system. A smart grid is an intelligent, digitized version of a traditional electricity grid. It uses big data, communication networks, and automations to monitor, control, and optimize power flow from generations to consumptions. So, what's a big data's role here? First, it enables real-time monitoring and control. With sensors across the grid, from power plants to your home, data is constantly being collected and analyzed. Second, smart grid rely on big data to predict and respond to the challenges. And third, the smart grids are crucial for integrating renewable energy sources like solar and wind. A smart grid helps to reduce the outage and downtime by proactively identifying weak points or faults. One of the biggest challenges in the integration of the renewable energy sources like the solar and wind is the One of the biggest challenge here is integration of the renewable energy source like solar and wind into the power grid. The key challenge is variability. You know that unlike the fossil fuels, you cannot control when the sun shines or the wind blows. That means renewable outputs is often unpredictable and intermittent, which makes balancing supply and demand much harder. This is where the big data plays an important role. First, we use data to forecast energy production based on weather patterns. For instance, by analyzing satellite imagery, wind speed data, and temperature, machine learning models can predict how much solar or wind will be available in next hour, day, or week. Then, big data help with balancing renewable inputs alongside traditional sources like coal, gas, or hydro. And it allows for the seamless integration of the renewables into existing grids, which are typically designed for steady centralized power generation. It also helps us reduce our reliance on fossil fuels by allowing the renewable to play a larger role in energy mix without compromising stability or reliability. So renewable integration supported by a big data is what makes the transitions to sustainable energy systems possible, and a smart grid technology ensures that variability doesn't become vulnerability. Now, let's talk about one of the most drivers behind the big data analytics in power systems, the environmental impact. Big data play an important role in advancing sustainability efforts across the energy sectors. First, it enables monitoring of emissions from power plants in real time. Second, it helps optimize how renewable energy is used. For example, if solar and winds are valuable, analytics platforms can prioritize their usage over the fossil fuels. And we have some key benefits here. First is compliance with the increasingly strict environmental regulations, especially in regions where carbon pricing or emissions caps are enforced. And equally important, it helps promote clean energy adoptions by demonstrating real-time gains in efficiency and cost saving and emissions reductions. To wrap up the discussions, let's look at how artificial intelligence is shaping the future of the power system. AI is not just a tool, it's becoming a core component of modern grid management. Its primary role is twofold. First, it enhances the predictive capabilities, allowing a system to anticipate faults, forecast loads, and so on. And second, AI automate decision making in scenarios where time is critical, like fault detections or demand response. AI enables near instant reactions and improving reliability and efficiency. Now, let's highlight some emerging trends that are driving innovations. Digital twins, the first one. There are virtual replaces of the physical power system. They use real-time data to simulate and analyze the behavior of assets like transformers or substations. Next is self-healing grids. Using AI, grids can automatically detect faults, isolate them, and reroute the powers. And blockchain for the energy trading. AI combined with blockchain supports secure and decentralized peer-to-peer energy trading. And this is especially useful in microgrid where prosumers can sell their excess energy to the neighbors. As we close these webinars, let's touch a critical component that is important for everything that we discussed so far. The role of the policy and regulations in big data analytics for power systems. Policy ensures that the use of the data in the energy sectors is ethical, secure, and accountable. With the rise of the AI, IoT devices, and advanced analytics, it's important than ever to establish a clear boundaries around how power data is collected, to protect the consumer rights and privacy. Smart meters and connected devices gather a lot of data about individual households and businesses. Second, strong policy frameworks are essential to ensure cybersecurity, especially as the power grids becomes increasingly digitalized and interconnected. Some of the key focuses areas in this space you can see here. First is digital privacy regulations. For example, we have a GDPR or Australian Privacy Act, which is defined how personal energy data should be handled. Or we have some cybersecurity standards for critical infrastructures to prevent unauthorized access or malicious trades, and policies that incentivize renewable energy adoption, such as subsidies for the solar installations or data-driven energy trading platforms. Let's take a moment to summarize what we've explored today. We talked about highlighting how big data analytics is transforming power system. Then we talked and looked at how machine learning is at the heart of these advancements by talked about different types of machine learning and algorithm, looking into the future, the energy sectors that are shaping by the AI, digital twins, and privacy and cybersecurity remains top concerns, especially with increasing connectivity. Thank you. That brings us to the end of today's sessions on big data analytics in power systems. I hope this webinar has given you useful insights into how big data and machine learning are reshaping the way we generate, manage, and distribute energy. Thank you.
Okay, thanks very much. And I just want to quickly apologize for those who had issues with the slides. Maybe just for future, just check, just try to click on the sync button. If it doesn't work, try to log out and log in again. And then there's a question here, Said. One of the guys wants to know, based on your experience, is it possible as an engineer to quickly get involved in big data application with basic knowledge of Python?
Yes, with basic knowledge of the Python also can work and can integrate the machine learning applications.
Okay, and then I see there's another one. In mechanical engineering, how is it the big data analytics in power system correlate with it?
Honestly, I'm not familiar with the field of the mechanical engineering, so I couldn't answer this type. Yeah.
Okay. There's another one. Just a sec.
I can see some questions here about the is there training on SCADA on monitoring MV networks and data analytics? Yes, there are training programs available that focus especially on SCADA systems for monitoring medium voltage networks and data analysis. This, I think this course At EIT, we have some courses about SCADA and industrial automations. I can see another questions here. That is there standardized organizations governing big data process or practice? Yes, there are several well-organized bodies and frameworks that provide guidelines, standards, and best practice for managing big data responsibility. For example, we have ISO or IECTJ-ATC committee, which focus on information technology. Any other questions?
I'm not sure if you saw this one. What is the scope of big data when it comes to cybersecurity?
Oh, sorry. We discussed about this one, about the cybersecurity. We need to be careful about the different parts of the data because the security of our data is really important in our applications. I can see one question here. To what extent has this use of the big data reduced reliance on fossil fuels in countries that have implemented it? Okay, in the country that have actively implemented a big data analytics in their energy systems, I think we can say like Germany or US or some part of Australia, we've seen a clear reductions in reliances on the fossil fuels, and largely due to the smarter integrations of the renewables. Because big data allows a system to forecast solar and wind availability, and then it's subsequent to balance the loads dynamically and dispatch the energy more efficiency. And this means grids can rely more heavily on variable renewable source while maintaining the stability. Okay, thank you. I think we have so many questions to answer, and but it's out of the time now.
Yes, thanks.
I can answer a few things, but I'm not sure that we have the policy on it.
And I will share our email address. So if you have any further questions, please feel free to just send them through, and then we'll pass them to the lecturer. And some of the courses that were covered in this topic, we have a Bachelor of Science in Electrical Engineering, Industrial Automation, Masters in Electrical and Industrial Automation. If you are interested in seeing some of our upcoming courses, we have that. I can actually send you this link, then you can just read more and just see what courses we have on the schedule for the rest of the year. And then, for those who have been asking me about the QR code to request the certificate of attendance. So first thing first, if you are able to scan the QR code, you can do so. Otherwise, I will provide you with another link. Thanks, Sepi. Otherwise, you can follow that link in order to claim certificate of attendance. Just gonna paste it now. Right. Alternatively, you can just follow the link that I just posted in order to claim your certificate of attendance. Just make sure that you complete the form and you send it to our webinars team, and then they will be able to assist you. And then once again, thanks very much. And for those who have questions or any feedback, we would really love to hear some of your comments. So feel free to send us an email, and then we can be able to just see how we can help you, and also some of the comments that you might have. Once again, thanks very much. Thanks to our presenter, Saide. Thanks very much.
Thank you. Thank you for all. Thank you all for your time, attention, and interest. And if you have any questions or would like to discuss a specific topic further, feel free to email me. Thank you.